Today I'm going to talk about a secret-free hypervisor and how we should rethink isolation in the age of speculative execution attacks. The scope of this talk is about speculative execution, and it's about how we restructure the hypervisor to minimize the surface and to build a comprehensive framework against similar attacks. This is not about trusted execution environment, not about enclaves, or distrusting and privileging parts of the hypervisor. The motivation of this work is that we live in the epidemic of speculative execution attacks, and we repeat the cycle on the right all the time. So we find a new vulnerability and we develop mitigations. And we deploy the mitigations and we suffer from performance degradation, and the whole cycle repeats. So we keep asking ourselves, is this the best we can do, and is there a better way to break this cycle? We think the cause of this problem is that we constantly call these vulnerabilities hardware bugs, but as the saying goes, it's not a bug, it's a feature. The reality is that our software isolation model does not match reality. We constantly refer to the architectural documents from hardware vendors, and we think that the architectural isolation is sufficient. And we keep writing software the old way. But the reality is that boundary has been broken, and those vulnerabilities, if we think them as bugs, then it's not really helpful, because bugs should be outliers. They should not be the norm, and they should be fixed. And after fixing it, we should not really think too much about them. But the reality is, we have to constantly think about those vulnerabilities when we program low-level software. So this prompts us to rethink how we write low-level software like Hypervisor. We first define what are secrets. So secrets are guest memory and register state. Of course, this definition is relative. Guest memory and register states are not secrets to their owners. For example, an attacker can review its own memory and registers via speculative execution, but it does not violate the definition of a secret-free hypervisor. So, what's wrong with the existing hypervisor designs? First is that a hypervisor design presents a massive surface, like the one on the right. We have hypervisor code and data, and we keep all the secret data structures from all domains and vCPUs inside the giant hypervisor space, and we have a direct map which usually maps to the entire physical RAM, so a massive surface is even an understatement. It is literally the entire surface. And we should rethink this strategy. And is this really necessary? The second thing is that we keep a deny list of all the hardware bugs, and we audit all the potential vulnerable secret data structures inside the hypervisor space, and we carefully audit them, and we block vulnerable ones with speculation barriers. Can we do an allow list approach? So we have a minimum space. We include the hypervisor code and data and some initial stacks. We start from there, and we add non-secrets to this minimum space instead of removing vulnerable surfaces from a giant hypervisor. And we should also rethink hypervisor guest isolation. We've seen from all those speculative execution attacks that the traditional hypervisor guest isolation boundary is broken. And we should also try to maintain secret isolation even inside the hypervisor space. The goal is that no secrets are visible even inside the hypervisor space. So let's rethink our strategy and use an allow list approach instead. We start from the bare minimum by having initial hypervisor image and data and some stacks. What makes this work different from state-of-the-art is that we don't identify secrets that need to be blocked from speculation. We identify non-secrets that are safe to speculate and can be added to this minimum hypervisor space. For example, host descriptors like x86, IDT, GDT in the hypervisor, MMO mappings, and generic scheduler state. They are not related to guest secrets. um, which means that they can be safely added to this hypervisor space. We also make the distinction between hypervisor allocation and its visibility. What it means is that whenever the hypervisor allocates memory, it is not automatically visible to the hypervisor space. And this will be elaborated further. So we should also maintain secret isolation even inside hypervisor space. What do I mean by that? Traditionally, we spend a lot of resources enforcing isolation in the guest space. We make sure they are properly isolated, but once we enter the hypervisor, we just somehow assume there is just a magic barrier that can guard against all the guest state from affecting hypervisor execution. But we've seen from all those speculative attacks that this is no longer true. We redesigned the hypervisor so that it's divided into multiple secret levels. So you have the global non-secret level, you have the domain secret level, and these data structures are visible to vCPUs of this domain only, and you have the vCPU level, which is only visible to this vCPU. Remember in the previous slides, we say we make the distinction between allocation and visibility. After making a hypervisor allocation, the hypervisor makes another call to decide on what level this data structure is visible. Is it non-secret? Is it domain secrets? And is it vCPU secrets? And the hypervisor uses page table isolation techniques to make sure these secret data structures are only visible on their corresponding secret levels. With this design, whenever a guest enters the hypervisor, it is guaranteed that it only sees secrets belonging to itself. And it is safe to relax some speculations because it's guaranteed that there's no secrets to other domains, and there are no secrets there for a malicious guest to speculate. There are challenges, quite a lot of challenges of this work. And I'll give you some examples. For example, we say that we start from the bare minimum and treat hypervisor stacks as non-secrets. We have the bare minimum of hypervisor code and some initial data and stacks, but it turns out stacks must be treated as secrets as well. For example, on hypercalls and on interrupts, a guest state, the guest registers frame is built onto the stack alongside with vCPU information. And we have to move hypervisor stacks to vCPU secrets. And this breaks a lot of things, and because the hypervisor code really assumes that all data structures should be visible to the hypervisor at all times. And there are other challenges like a direct map that maps the entire physical memory is of course against the principle of secret-free, but it is there for a reason, because with a direct map, the hypervisor can access arbitrary physical memory by just doing some bit shifting from the physical address to give you a direct map virtual address. And it is also usually contiguous mapped with huge pages, which usually reduces quite a lot of the TLB pressure. But how do we access arbitrary physical memory without it? And especially, how do we do that efficiently? And how do we match the efficiency of a direct map? These are some of the example challenges, and the answers are presented in the paper. Now we move on to the evaluation of Secret-Free Hypervisor, and we evaluate the Xen implementation. Overall, we've seen that in I/O intensive micro benchmarks, we've seen a slowdown of only 2.6% versus the 10% of enabling Xen default mitigations. And in real-world applications, the slowdown is almost not noticeable versus more than 1% of Xen default. So from the implementation and evaluation, we have a couple of important insights. First one is that if we can guarantee in the hypervisor space no secrets are visible, then we can relax some speculation barriers, because it is guaranteed that no matter how the speculation state is affected by the guest, there's simply nothing in the hypervisor there for the guest to speculate. This gives us reduced hypercall latency versus state-of-the-art mitigations. Especially this improves the performance in I/O intensive workloads. There's another key insight, which is that Xen also supports the para-virtualization mode, which is used on hardware without hardware virtualization support. This puts the Xen hypervisor in ring 0 and guest in ring 3, which also means guest and the Xen hypervisor share the same page table. And this creates a big problem because on meltdown vulnerable hardware, you then need to deploy page table isolation against meltdown attacks. And this gives roughly and sometimes even more than 50% of the overhead. But if we can have a minimum hypervisor space and we always stay on this minimum space, then there's no need for us to swap page tables. And this is still safe. And now, Xen parallel virtualization mode is usable again, even on meltdown vulnerable hardware. The secret-free design principle also defends against certain architectural attacks as well. For example, for the return to direct map attack, a guest can simply inject code and data inside guest space and find a vulnerability inside the hypervisor to redirect code execution to onto the direct map alias. But with a minimum hypervisor space, we add another layer of defense against such attacks as well. We've implemented the secret-free principle on other hypervisors and kernels as well. For example, we have a Hyper-V implementation, which has been deployed to Azure since 2019. And the Hyper-V implementation has gone through the test of time. It has been thoroughly production tested. We also have a Beehive implementation, which is a Type 2 hypervisor inside the FreeBSD kernel. And of course, we have implemented this on the FreeBSD kernel as well, which is a Unix kernel. The secret-free hypervisor idea works best on Type 1 hypervisors. On Type 2 hypervisors and the Unix kernels, there are a couple of caveats. And we have introduced a couple of proof of concept optimizations for them, which are elaborated in the paper. What is quite exciting is that this work guards against categories of attacks and even against unknown attacks. After the paper was accepted, branch history injection was disclosed. It circumvents existing IBRS defenses, and we repeat the cycle again. We need to develop mitigations. We need to coordinate with the industry for the deployment of mitigations, and we suffer from some more performance slowdown. But a secret-free hypervisor is well prepared against that because we simply don't assume that there is just a magic barrier between hypervisor and guest. We assume that guest speculative execution state can leak into the hypervisor, but we properly isolate secrets, even in hypervisor space, to guarantee that there's simply nothing for a malicious guest to speculate anyway. So we are actually well prepared against branch history injection, and we don't need to develop specific mitigations in a secret-free hypervisor. So the conclusions of this talk are first that current defenses against speculative execution simply don't scale. And our programming model for writing low-level software no longer matches reality. And the isolation barrier between hypervisor and guest is already broken by speculations. A hypervisor should embrace a secret-free design by having a minimum space, by using a allow list approach, and by also properly isolating secrets even inside the hypervisor space, to guarantee that secrets are not visible, not only in guest space, but also when a guest enters the hypervisor. This is a systematic defense against categories of vulnerabilities and even against unknown vulnerabilities, like the branch history injection attack we've just mentioned earlier. This shows better performance than state-of-the-art mitigations because we allow speculations in paths where secrets are guaranteed to be invisible. And this is a generic approach, which is also applicable to multiple types of hypervisors and kernels, including Type 1 hypervisor, Type 2, and also Unix kernels. And thank you very much.
Okay, thank you for that very nice talk. I think we have time for one quick question.
Hello, Marius Meltzer, my name. I'm working in my job on microkernel-based operating systems, concretely on L4RE. And my intuition would be that all this domain isolation would already be present in a microkernel-based operating system using some kind of micro-hypervisor. Did you have a look at these systems? And if yes, do you know if there's still work to be done, or if this would be a good opportunity to just switch to such a system?
Can you hear me?
Yes.
Can I be heard? Yeah. So actually, I actually started smiling because this is exactly what one section of the paper is talking about. So one challenge of this work is that why Type 2 and Unix kernels don't work that well is that they're just monolithic kernels, and really introducing the idea of domain private or DC private memory is super difficult. It requires tons of code lines of changes. So actually, in one section we discussed, if you properly isolate the kernel components, especially you put those in charge of secrets and those in charge of non-secrets, probably separate them and have a microkernel approach. That will make adopting a secret-free hypervisor super straightforward. In one of the sections where I'm just calling to people, please think about the microkernel approach. Yeah.
Okay,
thanks.
thank you. Great. We have to move on to the next talk. Thank you.